type of attractive force is an intramolecular force called ionic bonding. Now remember, in an ionic bond, you have metal and a nonmetal with a positive and a negative charge. And so here are some of the characteristics of ionic bonds. The first is that as solids, they do not conduct electricity, and that's key. When they're dissolved in water, however, they do conduct electricity, and that's because when they're dissolved in water, their ions are free to move about and to conduct electricity. They're not held tightly in a solid, and therefore the flow of electrons is much easier because the ions themselves are free from that rigid solid. The next characteristic is when they're solids, because there's a really strong attractive force, they have very, very high melting points. So just as an aside, since I've now talked about ionic bonds, we're going to really quickly discuss factors that affect the strength of ionic bonds. So the first thing for you to know is Coulomb's law. Now, Coulomb's law states that the larger the charge of an ion, so +2 is a larger charge than +1, and the shorter the distance between the nuclei of the ions, the stronger the bond, the ionic bond is. Well, that attraction, that bond energy, when we're talking about ionic bonds, we call that the lattice energy. So the higher the charge and the shorter the distance between the nuclei, the stronger that attraction is, the stronger that lattice energy is. Well, how does that translate into actual ionic bonds and being able to compare the strength of ionic bonds for different ionic compounds? Well, the first thing is the charge. Okay? So the higher the charge of an ion, the larger the charge, the stronger the bond's going to be. So if I were to compare the ionic bond of sodium chloride, NaCl, versus magnesium oxide, MgO, since magnesium and oxygen have a +2 and -2 charge, that tells us that the ionic bond is going to be stronger for magnesium oxide versus sodium chloride, which only has a +1 and a -1 charge. The other factor that affects the strength of ionic bonds is the size of the ion. Okay, so for example, if I were to compare the strength of sodium chloride and lithium fluoride, if you notice, lithium and fluorine ions, they are smaller than sodium and chlorine, which tells you that lithium fluoride is going to have a stronger ionic bond. It's going to have a higher lattice energy because they are smaller ions. Now the question becomes, well, what if they have a different charge and a different size? Well, charge is the ultimate decider in it. So if they have different charges, if two ionic compounds have different charges, charge is the most important thing. So if I were to compare lithium chloride, for example, and magnesium oxide, since magnesium and oxygen have a +2 and -2 charge, that takes precedence. The size of the ions does not matter. However, if your ions in your ionic bond have the same charge, then you go and compare the size of the ions. So those are questions that you'll see a lot, and you can also see in the real world when you're comparing the strength of ionic bonds, specifically when we're looking at melting points and boiling points, even though we're really not going to see an ionic bond, an ionic compound melting or boiling, but if we would be able to determine which would have a higher melting point or a higher boiling point just by comparing the charge and the size. Specifically, the stronger the ionic bond, the higher the melting point or the boiling point would be. Metallic bonds exist when you have metals. So here you have gold, and the way that we describe metallic bonds is that we say it is an electron sea, meaning that you have a bunch of gold atoms, and instead of sharing or donating their electrons move freely through all of the different metals. And so it's a C model. Now let's look at some of the characteristics of metallic bonds. The first is that they have a high melting point, not as high as ionic bonds, but still a high melting point. It takes a good amount of heat to melt a liquid. And they are great conductors of electricity when they're solids. And so that's how they're different from ionic bonds as well, because they're great at conducting electricity even when they are solids. Covalent bonds, there are going to be two different types that we look at. The first that we look at are just molecular solids. Molecular solids are discrete molecules like carbon dioxide or any of the other molecular compounds that we've looked at. And so when we're describing characteristics of molecular solids, what we use to describe them and to dictate what they're going to act like, we look at their intermolecular forces, which includes hydrogen bonding, dipole-dipole, or London dispersion forces. Remember, hydrogen bonding would have the highest melting and boiling points, while London dispersion forces would have the lowest melting and boiling points, simply because London dispersion forces are the weakest type of intermolecular force. So those are molecular solids. The last characteristic is that they cannot conduct electricity, period. No matter, even if you try and dissolve them in water, which unless they are polar, you aren't able to, but they do not conduct electricity. The other type of covalent bond, the other form it can take, is in the form of covalent network solids. Now, covalent network solids might sound new and unusual, but you've actually had a lot of experience with them. They have an extremely high melting point, and they have an extremely high melting point because, as you can see, for example, for diamond, a covalent network solid consists of atoms that are all tied together by covalent bonds. It's not a molecular solid in which there are covalent bonds, but then they rely on intermolecular forces. All of the attractions in a covalent network solid are the intramolecular force of covalent bonding. And so as a result, they have a very, very, very high melting point. And two examples that you see on a daily basis are diamond and graphite. Now, really just as a quick aside, graphite it looks way different than diamond. It's an allotrope of diamond, meaning that the bonding is just slightly different. And the reason why is the covalent bonding exists in layers between those carbon atoms, but then there are actually gaps. And as a result, graphite forms sheets, as opposed to diamond, where all of the carbon atoms are attracted to one another. So that's why graphite's so easy to use to write, because those atoms will simply move past one another very easily, but still extremely high melting point. So if we're comparing melting points, covalent network solid has the highest, followed by ionic, followed by metallic, and then followed by covalent. As far as conducting electricity, metallic is the one that conducts electricity as a solid. Ionic will if it's dissolved, but the other two will not.